Hello. Hello, can you hear me? Yeah. Let's get started again. I hope you all enjoyed the lunch break. As I said this morning, we have a very nice lineup of keynote speakers, and the one that comes next is no exception to that. So we're really happy to have Jakob with us. Um, he's an authority in multi-agent reinforcement learning. So that's what he has been working on for quite a while. He's at University of Oxford. I guess he did his PhD there as well. Then moved to a couple of different places. Got some best paper awards, an ERC grant. Has his lab in Oxford, and will talk to us today about reinforcement learning and how to scale things up. So I'm very curious, and I leave the floor to you.
Cool. Yeah. Thank you. Thank you. Thank you for having me and for the very kind introduction. So I don't know about all of you, but it's a hot day. We're indoors. Everyone's getting tired. And I would like to avoid that. So what I would suggest today is, I mean, I can make this a sales pitch. I can talk to you for an hour and get you really excited. And you're going to be working on Jax. But why do we not do that? Why do we instead just have you ask questions, make this a bit more interactive? Can I have a show of hands? Who is in for that, of making this a bit more of an interactive seminar? Awesome. That's, I mean, like a third, probably. And that's right. And I think a third is about what we need to make this fun. Cool. So yeah, I'm Jakob Foerster. I run the Foerster Lab for AI Research, sometimes also referred to as the friendly lab for AI Research. And I will try and convince you today that we're in the middle of a revolution that very few people know about, and that hopefully in the next hour, you'll become one of the insiders who will understand what this means for our field. And when I say our field, I mean people who do reinforcement learning, which might not apply to all of you, but maybe it will by the end of this talk. The outline of my talk is as follows. I will talk through what I mean by the hyperscale revolution of deep reinforcement learning. I will then talk about the first things that this allowed us to do at Oxford, which is to build blazing fast environments for multi-agent and open-ended learning. In the second part of my talk, I'll then talk about scalable meta-reinforcement learning. So how does this revolution allow us to actually tackle questions that were far outside the realm of academic compute in the past? And then if we have time, I will talk about PQN, our recent reinforcement learning algorithm that brings back Q-learning to the forefront of machine learning research. All of this work would be completely impossible with all of these fantastic people. So here's a small selection of the folks at Flair. This picture was taken last week at Vienna during ICML. So if you're wondering why my voice is as it is because of this conference. Wonderful. I'll start out by talking about a tale of two different revolutions. So you probably all remember in 2012, AlexNet was launched. And there was a crucial aspect of AlexNet, which was it used GPUs efficiently. And what this resulted in was an unbelievable drop in the top 5 error rate, more than 10 percentage points lower than the runner app, right? And this had been a challenge we had been working for decades to make progress on this. Shortly after, actually, within a year and a half, the deep reinforcement learning revolution started. Previously, people had been working on tabular settings, had been working on small problems, and suddenly, after DQN, we could start working on high-dimensional, complex settings. And at that point, there was a sense of optimism. We have the tools now to build AGI. From now on, everything is reinforcement learning, because it's the one framework that solves it all, at least if you account for continuous learning as well. However, let's look back about 12 years later. By all measures, DQN was a success. We have about 45,000 citations if you add up these two papers. But let's also look at AlexNet, 158,000 citations. And obviously citations are a terrible metric, but we all know that supervised learning, deep neural networks have revolutionized the world, and this journey is still going on. Doesn't matter if you think about LLMs, about chatbots, computer vision. So there's a key question to ask here, which is why did one of these revolutions actually change the world forever, while the other one has been so far mostly a paper mill to a great extent, and has not had the real world impact that all of us expected. And I'm going to put forward a claim here, which is that reinforcement learning suffers from a computational efficiency problem. And that is because we have to run the agent on the GPU because it's a deep neural network. In contrast, our environments are running on the CPU. And what this means is you don't just have to pass forwards and backwards information between the CPU and the GPU, but you also have to create complex algorithms that can schedule the CPU and the GPU to try and get around this fundamental problem. In contrast, if you're doing supervised learning, it's quite easy to keep your GPU busy. All you have to do is make sure you feed enough data. It's forward, backward, forward, backward, forward, backward, right? So that's a fundamental concern. And a lot of the field has been trying to get around this concern by building complicated algorithms that use the CPU and the GPU and shuffle data around. So for example, here's batch A to C. You can see there's different actors. There are forward pass, backward pass, environment steps. It's difficult to keep synchronized. There's Impala, which again had another approach to all of this. And the issue with this is data gets stale. So you have to work around the fact that data is no longer fresh. And you get a lot of algorithmic and engineering complexity, which I think has been really holding back the field. So what did this mean in practice? Can I have a show of hands of those of you who know Hanabi, the card game? This is a game I've worked on a lot. If you care about theory of mind, multi-agent coordination, I highly recommend looking at this work. I will not talk about it today, but I will use it as a benchmark because I've worked on it for a long time. I can compare what we've done in the past and what is possible today after this revolution. And basically, you could pick your poison back in the day. The options was either you're going to be extraordinarily slow, taking 7 days on NVIDIA V100 GPU, which comes down to 165 steps per second, right? That's extraordinarily slow if you work in deep reinforcement learning. 7 days to run an experiment. Or you could be extremely expensive. So we could run agents for 20 billion steps, but that would cost us 100 CPU years. And if you do the maths again, you get around 190 steps per CPU second, right? And you might ask, who runs experiments of that scale, spending 100 CPU years on training Hanabi agents? And you'd be absolutely right to think this was done at DeepMind during an internship. There was a way around this, and that was you could actually make it fast. You could hyper-engineer it. Rather than Hyperscale, you could hyper-engineer. You could implement everything in C++. And if you're good enough at implementing a training loop environment and all of this in C++ and making sure the multi-threading works and everything is efficient, you could actually get to around 12,000 steps per second on 3 GPUs, much, much faster. That's something we did with a lot of engineering support with brilliant people during my time at Facebook. And this is the architecture that you get, right? So probably not something that's easy to replicate or easy to build upon as an academic lab, right? It was sort of alien technology in terms of what it could accomplish. So the takeaway here is deep reinforcement learning had lost the hardware lottery. And this is really, really bad for anyone who builds on top of reinforcement learning, right? So for example, if you care about meta learning, continual learning, multi-agent reinforcement learning, all of these places, you're going to use reinforcement learning as an inner loop, as the starting point, the foundation of the work. And lo and behold, if that foundation is expensive, slow, and brittle, probably it's going to be very, very difficult to make progress. And this has been actually an excuse for many people. Because if you're a researcher in this field, the good news is you don't have to blame yourself. Because losing the lottery is nobody's fault, just the random luck of the draw. However, that excuse is about to be ended because there is a way forward here. And that's what I call the second coming of the GPU to deep reinforcement learning. Wouldn't it be absolutely brilliant if you could just run all of it on the GPU, including our agent, like we're doing before, but also the environment, the loss computation, and the training loop. Rolling out actions in the environment on the GPU, keeping all the data there and train the agents on the GPU. Wouldn't that be brilliant? Actually, can I have a quick show of hand? Who knows about reinforcement learning? Okay, I think you all, is anyone confused at the moment? Is everyone sort of on track, like knows where we're headed? Any questions so far? No questions. Brilliant. Sorry, yes. I'm saying if you're building, great question. The question is, do you really need RL to do meta learning, continual learning? What I mean here is if you're doing meta reinforcement learning, continual reinforcement learning, please remember I'm, to me, all learning is going to be reinforcement learning at some point, because it's a solution to everything. But obviously, I fully respect and endorse anyone who's not doing reinforcement learning so far, because you didn't know this existed. I do hope you'll be convinced to start working on reinforcement learning after this talk. So wouldn't this be brilliant, right? And the only issue is that this used to be really, really hard, because programming CUDA is difficult, right? It's the last thing many of us want to do. And the good news is there's a solution to this, which came up a few years ago, and that's called JAX, right? So what JAX allows you is to have a lot of the benefits of GPU native programming. So for example, just-in-time compilation, or vectorization, or differentiation, and parallelization. But being able to do all of this in a Python framework, being able to program in a language that is much more sort of usable for many people who are doing machine learning. And this was fantastic. And furthermore, it has a functionality which allows you to easily add a batch dimension and blast out any code you're writing across the different GPU cores that you have. So it's very, very easy to parallelize your code. This has really been a huge change to the way that we do research, that we think about research, that we think about what problems are tractable and academic compute. So here's a little meme from my student Chris Liu, who pioneered a lot of this. You have normal reinforcement learning training. It's pretty cool, but it's slow. Multiple environments on the CPUs, vectorized environments on GPUs, and then end-to-end vectorized reinforcement learning on GPUs. And this actually has been gaining popularity recently. There's about 500 stars now on this repo. But more importantly, it's really sped up the way that we do reinforcement learning. So what you can see on this graph is the time it takes to train a single CleanL agent on Cardport. CleanL was a reference library for everyone doing reinforcement learning. And that's about 180 seconds to train one agent. And then on the y-axis, you see that how many agents we can train instead in the same budget using end-to-end JAX, right? So you get this speed up of, factor of, even by half the time that we've trained a single agent, we've already trained 2,000 agents in parallel using JAX, right? This is a 4,000, roughly factor of 4,000 speed up that you get. And if you think about this, suddenly you used to have one GPU. Now it's as if you had access to 4,000 GPUs, right? There are not many labs that have 4,000 GPUs all wired up running synchronously, right? So this is sort of mind-boggling. And in the rest of the talk, I'll talk through some of the things we've done using this advance in technology. And obviously, you can't do any of this unless you have environments that actually run on JAX, right? Unless you're able to take advantage of having JAX implementations. And the first thing we did, because was introduced, I come from the multi-agent world, we introduced a suite of environment called JaxMal that has 8 different standard benchmarks, all implemented in JAX. And these run blazing fast on the GPU. You'll get many more of the same graphs. So for example, here's a multi-agent environment of Brax, of control tasks, the multi-particle environment, overcooked, Storm, these are general sum learning, and there's Hanabi. So if you'd like to work on this while being fast and efficient, you are more than invited. And this is more of the same. So we've basically got these orders of magnitude of speed up, which will be the common theme. I won't keep repeating it. Just remember 1,000 to 10,000 times is what we get in speed ups across doing this work. We did also introduce a new environment, and obviously, the Stack of Multi-Agent Challenge was very, very popular as a test bed for multi-agent learning, but then saturated. And the issue is you had to run the actual StarCraft game. So what we did instead is we implemented something that has a symbolic version of the same challenge, where we can simulate all of the different unit types and, but we can run it on end-to-end GPU acceleration, right? Now, obviously, this one looks much more interesting. But remember, when people work on this game, they don't work on pixels. They do work on the symbolic representation, which looks very much like this, right? So there's a tendency in our field sometimes to be fooled by flashy graphics, but actually the work that people have done has been on the symbolic representation of this problem. And this is really, I think, quite unique about this approach, that we now have a benchmark that combines speed, ease of use, and a wide range of environments. Just to make that point, I earlier said the C++ end-to-end version that was difficult to engineer did about 20,000 steps per second. We can now achieve 370,000 steps per second on Hanabi. So what this means is you can train for 10 million steps in, I think it was 10 hours, right? So experiments that were extraordinarily hard to do or impossible are now easily possible. So the other thing we did, does anyone here work on open-ended learning? Anyone interested in this? Because I can also speed through this. So open-ended learning is this, I think, quite an interesting emergent field about how to build agents that can solve a broad variety of different tasks. And we developed a new environment based on Crafter called CraftAx. CraftAx is a reimplementation of this sort of Minecraft-style game in Jax, and it is extraordinarily complicated. It has procedural generation of different floors. It has this sort of like nice feature that you can, at any point, the agent can die. You can also study lifelong learning in this environment. And there's this very, very difficult progression through different dungeons. And it's really a good test bed for deep exploration, skill discovery. And you can imagine if you want to go through here, and the agent has to go and build things and plan and do long-term reasoning. And because everything is generated procedurally, you never see the same environment twice. So the agent also has to generalize. So this was a spotlight at ICML last week. And part of the appeal, again, is that this is extraordinarily fast. So we get to 1,000 steps per second, and it scales really nicely as you parallelize across more workers. So this is, if you ever have a student or a collaborator says the problem, we're running out of problems to solve in reinforcement learning, point them to this. We do have problems to solve, and they're actually really hard right now, because if you look at the performance, we can sort of measure how far the agents get. Do they achieve the basic accomplishment, intermediate, advanced? And all the methods we have right now are flattening out at intermediate scale. No agent makes it to the sort of what we call the advanced problems in this benchmark. Are there any questions? And we like to claim that this is open-ended because you can actually do mining, farming, dungeon crawling. There are a lot of sort of different skills and capabilities needed in this environment. The next environment we built is JaxLife, which is an agentic simulator. So this is for anyone who's worked on A-Life, who's looked at the question of how do we simulate life on computers. This would be a great test bed. Previous A-Life simulations have actually been much more low levels. This is about modeling molecules or chemistry, but you can imagine it's quite difficult to get to a system of intelligent behavior if you're starting out from atoms. I mean, we know it's possible because the world runs on the level of atoms, but probably we don't have quite enough compute at the moment. Instead, we take a very different approach, which is we care about high-level intelligent behavior. This is about having agents that have simple fixed morphologies, but they can evolve the neural networks that describe them. And in particular, what they're able to, they can interact with these little robots. So the vision here is we as humans would like our agents to do the work for us, right? We don't want to be doing the hard work. We want to be sitting at the beach and drinking champagne. But wouldn't it be fantastic if our agents themselves could be supported, could learn to program robots around them to survive better? And what this allows you is to have a Turing-complete A-Life simulation, because these agents have the capabilities of programming each other, programming robots, communicating, and so on, all while minimizing flops to simulate irrelevant parts of the environment. So we're not simulating atoms, we're simulating the high-level flow of information, capability of programming other robots, and we're running evolution on the system. And in particular, these agents can plant and eat food. They can also gift and steal energy, and these robots can go and perform all the actions that other agents can perform, right? So in principle, you can get this high-level emergence of capabilities like coordinating others, like being able to build factories, like having an entire artificial society. I'll skip through this quite quickly, but a lot of this is done using attention because we want to have encodings that scale across different numbers of agents in the environment and so on and so forth. And we're trying to build off of the success of the transformer architecture. So I spoke about this briefly, but this is effectively the way that we've allowed these agents to program these robots, which allows, in principle, the emergence of these very, very complicated interactions. Now, you might be wondering how practically useful are these robots actually. So what we did is we hand designed within that action space that the robots have some behaviors. So for a start, you can see that these robots can push others. They can actually be used to transport things. They can also be used to communicate. So you can see that here there's a chain of communication that's being used to signal messages, again, using that same action space and API that the agents have. And they can do farming. So here we're using a row of robots to go in and terraform this blue land into food, green is the food. And all of this is done, again, hyper efficiently. Yeah, so this is Turing complete system. I set all of this, and we implemented this this 1D learning rule from the typical A-Life simulations, where you have this update pattern given the neighboring blocks, and this is all done using these robots as interfaces. So in principle, agents can actually learn to build computers, do information processing, do farming, build factories. All that is within scope for the simulator. This is what it looks like after a few simulation steps. So you can see these agents actually, they're fanning out, they're searching for food, they've learned to push each other across water streams, and they're surviving much better than previously. So this was very nice to see. It's a sort of first sign of emergent behavior. And we also had these kinds of scaling laws, where if you start out with a few agents, not very much happens, and then gradually as you move up the agent numbers, you get these sort of like large-scale patterns that emerge, where they start to focus their efforts on terraforming specific parts and utilize the fact that they can move around and build bridges and so on. So this was very neat to see. Are there any questions? I will now finish with a section on environment. Please. The robots allow for many more interesting behaviors. So in principle, so in this environment, agents can plant food, plant seeds. But the complexity of that behavior, like how optimally can you plant seeds? Probably not that optimally, but if you have robots, you can now get the robots to plant seeds on your behalf and harvest, right? So they allow the agents to actually learn to build sort of like a farming system, which could then scale the population of agents much bigger, right? So we have the agents in there to make the system open-ended in the complexity for survival. You know, the inspiration here was humans have learned. So the question was, why do you need robots, right? Isn't enough to just have agents? And the inspiration was we wanted to have something that allows for open-ended complexity, the emergence of computation, of maths. Oh, they're not teachers, they're programmable. So they're little bots that the agents can program. So here, if we look at the API quickly, so the agents can output an action, which will then go to the robots that the robots can then use as a program, right? So this is that's the main idea, and these robots have all the same actions that agents can take, but they're programmable by other agents. So this is it's the main way to build sort of, this is quite a limited computation stack, but the idea is they could assemble computation networks ad hoc, for example, to have more complicated computations and behaviors in this environment. Are there any more questions? Yes, please. So the question was, doesn't the parallelization also change which reinforcement algorithms you want to use? And the answer is yes, but I think often it allows, we have an example at the end of the talk, if we get there, where we actually use the fact that we know on the GPU and can parallelize to really simplify algorithms. And it's actually much better than what we were doing before. So that's the hope, that by removing the complexity of having the CPU and the GPU, we can greatly simplify the way that we do research in reinforcement learning and have more robust and simpler algorithms. There was another question. Yeah. So the question was, we have these agents, they can in principle they can evolve to learn all sorts of complicated behaviors beyond gathering food, like programming robots, like building artificial societies, like doing science. In principle, that is in scope, right? Have we gotten there? Like, no, we haven't. But I think I've shown you a few of the patterns that could in principle emerge in this environment. Question? Yes. So the question is, if you have a single agent and a single environment, I mean, I want to model online learning. What's the hope for this, right? And the question is, in my mind, why are we doing this, right? Are you trying to develop new algorithms? Are you trying to improve on something? You probably want to run a lot of different experiments. At least you can parallelize over seats. You can parallelize over other parts of your algorithm. You can meta-learn. I believe right now, sort of using this as a toolbox for research is amazing. Obviously, if you're deploying something in the real world on a single agent, a single lifetime, you're not going to use this, right? Should be very, very clear. This toolbox is fantastic if you're a researcher working on research, trying to understand and develop better algorithms. Once you deploy it, you probably will not implement your environment in JAX. Probably the environment at some point will be the real world. And you're not going to have a perfect simulator for the real world. Does that make sense? So it's for studying algorithms, improving algorithms, and doing foundational research in a way that is sound and flexible and repeatable. Any more questions? Wonderful. In that case, I would move on to the second part of the talk. We will change gears quite radically, which is to talk about meta-learning. And the first question we ask is whether learned optimization can make reinforcement learning less difficult. That was a question. It was at a workshop last week. We received an oral. And you'll know that reinforcement learning is basically impossible, right? You have non-stationarity, you have exploration exploitation, you have plasticity loss. There's a lot of literature that says it's very, very difficult. And a lot of papers that claim, how do we address this? And I think I have some questions in the Q&A. Is anyone in the Zoom? And could let me know? That would be fantastic. Great. So let's skip through this. We had this earlier quickly. I assume everybody knows stochastic gradient descent. I have some parameter vector theta, and I have a learning rate eta, and I have a gradient gt. And then there are popular versions like Adam that instead do some type of rescaling. They track the velocity and the momentum and try and get the update size to order 1. But all this seems quite hand designed. Wouldn't it be great if we could just learn the perfect update rule instead? And this is what we try to do in this paper, where we effectively parameterize an update rule that takes in the gradient and applies it component-wise. And the update rule itself is parameterized by a deep neural network phi, right? So there's a recurrent neural network that takes in one gradient after another, and then learns an update rule. And because people have been working so hard on reinforcement learning, we thought it might be good to have additional information rather than just the current gradient or the history of gradients. And we spent quite a lot of time trying to think about what else should this update rule actually condition on, right? And the reinforcement literature has come up with a lot of features that might be relevant. For example, plasticity loss, how many of your neurons are still alive, and so on and so forth. And that really allows us to say, we're just going to learn this. We're going to sidestep the need to design these optimizers, and we're just going to learn the update rule for reinforcement learning rather than having humans do all that work. Remember that agent I showed you, the human sitting by the beach drinking champagne and the robots doing the work? That's the vision here, right? The vision is we don't want to do the hard thinking part because theory is complicated and has left us in the dust. Nothing works still after decades. So why can't we just go and learn this instead? Now, you will all know that this implies a meta loop, right? So because I have my agent taking actions, I have the environment. And now what I need to do is I need to go in and say, well, for each one of these, for each of these possible parameterizations of my update rule, I'm going to run an entire learning loop of this agent over whatever it is, hundreds of thousands of episodes. And I get a final return, and that's the reward for the meta learner. And I'm going to update my meta parameters, right? Hopefully this is nothing new. And hopefully you would also agree that this is something that's completely insane, right? Because you're going to run this loop as often as you need to learn the parameters of your optimizer. And this is a deep neural network. So we're meta learning a deep neural network for reinforcement learning. And please, questions, fantastic. This is a brilliant question. Aren't you just going to learn something that's so specific to the one specific problem that you're learning, and the whole point of Adam is to be general, right? This is the elephant in the room. If you're doing meta learning, how do you make sure that you don't overfit to the one specific problem? And we'll actually get into generalization a bit later. The good news is that is quite a restrictive update rule. It's a small recurrent neural network. It only conditions on one parameter, one gradient at a time. So it's a parameter-wise, it's applied parameter-wise, not across many parameters at the same time. And it receives a few exascalar inputs at each time step. So we were quite careful to make this A, efficient, and B, also try and avoid the risk of overfitting. And I'll show you some evidence that this generalizes to an extent. Right? This is a fantastic question. Now, the question also remains, how do you actually learn any of this stuff? Because what a lot of people have done is they backpropagate it through time, right? So what does that mean? I'm going to unroll the computation graph of my entire reinforcement learning loop, 100,000 steps, and I backpropagate through it, and I do the higher order derivatives. And that's what this looks like. I have my states, I get my rewards, I calculate my learning loss, I get an update, and then I repeat this 100,000 times. And then I get a final reward, and I try and backpropagate through all of this. So you're trying to backpropagate through all the samples you collected during your entire training process. That's obviously expensive and unstable because we had this point earlier, backpropagation through time is expensive, more so if you have large learning loops, like in reinforcement learning. You could instead truncate this. So this means you're cutting the line. So you do 2 steps of unrolls, and then you truncate, you just backpropagate through here. And the issue with this is that you're going to have a lot of bias in this. It's obviously more stable, but you will acquire more bias. Does anyone have an alternative suggestion for what we might want to try instead? ES. Yes. Show of hands, who knows of ES? Evolution strategies. You've all missed out. ES is amazing. Did you hear what I said? Anybody else struggling to understand what I'm saying? This is useful feedback. Thank you. Raise your hands if you can't hear me, understand me. I don't know what the acoustics are like. I can hear myself just fine, but I don't know what the acoustics in the room are like. I'll try. I'm quite excited and have a lot of material to go through. So and actually speak up. Please raise your hand again and let me know if I speed up again. I will try and speak as clearly and slowly as I can. But ES is fantastic. If you don't know about ES, you've been missing out. And there's another thing that will change your life, not just Jax. It's ES. So what is it? Evolution strategies is allowed us to take a meta gradient, estimate a meta gradient without backpropagation. And this is crucial. Instead, what we're doing in ES is we're trying to estimate the gradient of the expected return of a fitness function around the distribution, around the normal distribution around phi from samples. And as it turns out, if you care about the derivative of the expectation when sampling around a vector phi, you can now estimate this as a weighted sum of the fitness phi evaluated at different noise vectors epsilon, weighted by epsilon. So by having a Gaussian distribution around the current parameter vector phi, we're making this differentiable and smooth in phi. And if you look at this, the only information I need is the value of the fitness for my different candidates, different noise vectors epsilon, and the noise vector epsilon, just the weighted sum. And that approximates unbiased the gradient of this fitness with respect to phi. And in particular, I don't have to differentiate through time. I don't have to do any gradients. I just need to take samples. So what this looks like in practice is we roll out the optimization with perturbed optimizers. So we sample around the current parameter vector phi of the optimizer. We parallelize computation using Jax because otherwise it's hopeless. And then we measure the final return of each of the optimizers. And then just sum up final return weighted by the corresponding noise vector for that rollout. And it's the entire training loop that we're running for that noise vector. Okay? And it's not biased anymore. It's now the correct gradient for optimizing the final return of a reinforcement learning agent when using that optimizer phi. Are there any questions on this? Yes. let me go back here. This is what phi is. Phi is the optimizer. For a given parameter theta at the learning step t, it takes in the gradient at time step t and additional information that we parameterize that we explain in the paper, like dormancy, like statistics about the weights to know the context it's in. And then it calculates how to best update the parameter theta of the learning agent. Theta here are the weights of the policy. Any more questions? So the question is great. It's sample based. If in high dimensional spaces, shouldn't you struggle? And we haven't actually found this. And the good news is if you have irrelevant dimensions, they don't change the fitness. So they cancel out, because what you do for noise reduction, you don't quite just do what I say, but you do what I mean, which is you actually do antithetic sampling by comparing the fitness at plus epsilon minus the fitness at minus epsilon. So if you have parameters that don't matter, that don't change the fitness, like you often have in deep neural networks, that will cancel out. And just practically speaking, we have not had issues scaling up ES. But everything else we've tried, we spent a lot of time trying to make meta gradients work in our settings. All these things have failed radically and drastically and entirely. It was completely hopeless. We had a project where there was one student trying to do ES. The project, it worked within a few days, and there was another student trying to do meta gradients, and it never worked out. Questions? It's a recurrent neural network. It's a GRU, LSTM, one of the two. We're suggesting delta theta, right? So we're learning in an increment to theta and it's applied parameter wise. So if you have a 10 million size parameter vector, we're applying this 10 million times, for example. It's parameter wise. So it's not a matrix acting on, it's not acting on a matrix, put on a matrix. It's acting on each individual parameter in turn. And it's receiving context beyond the gradient for that term in terms of its neighborhood, its position in the network, time through training, dormancy, how many neurons are still alive, and so on and so forth. So that it can learn a useful optimizer. Question? No, we're sharing the weights of phi. We're just applying it in parallel of all the different weights in the network. Because otherwise you would obviously drastically overfit, right? Otherwise you could just put out like, let's just think about this. If you had one recurrent neural network for each parameter theta, what would you learn, hopefully, immediately? Hey, what would you learn? Let's come on. Wake up, everyone. What's going on here? Go, 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 go. What do you learn? I give you one recurrent neural network per parameter theta, and we're running all of this because we're like, it's so flexible, it's so awesome, it's so meta. What do you learn? What's that? The identity. We're always adding theta to theta. Oh, so you're saying the optimal solution here? Oh, this is a good claim. I like it. So you're saying we're just going to learn the optimizer is just the identity. That's the claim. The optimal optimizer is the identity. Who believes this is true? Who believes that the optimal optimizer is just to say we're going to make theta t plus 1 is just equal to the gradient? Show of hands if you think this is true. Well, you just said it. You said identity, right? Where it's about what do we learn? What's optimal if I have one phi for each theta? Okay, what do you learn? What's the optimal optimizer for a fixed task? Sorry? The solution theta star. It's an amazing optimizer because it spits out the optimal value for theta at the first learning step. Okay, does it generalize? No, right? So that's why we don't do this. It's a great question, by the way. Thank you. We share the weights phi across all the different parameters, and we'll get to that in a bit more detail, what that means. Any other questions? These are great, by the way. I much rather you ask all these questions than being confused, because that's a waste of everyone's time. Yes. You just have to trust in the computers. You know, this is in, and we actually had to do a little bit of stabilization because you can imagine if you add noise, high dimensions, things can go weird. So there's a bit of normalization that we do, but there's no guarantees. We never regularize it. We just say this is what it is. Yeah, then you're fine, but you've also learned a very restrictive update rule, right? So here what we're trying to do is we're trying to really automate a lot of the machine learning process. Um, sure. But you're allowed to feed in extra things. For example, you're allowed to compute the correlation. If you're concerned about this, and this is what we did in the paper, right? We just think about like what information is useful that we could feed in addition. We just calculate it, we add it, let it conditional and figure out what to do, right? So I said this before, dormancy, activations, like statistics, population statistics, all these things, we just feed into the optimizer and let it meta learn what to do with it. Really good point. What do you do if you can't even do curvature, for example, right? Any more questions? Yes. Oh, the great question. So we use the recurrent neural network. Have we tried a transformer? We haven't. I encourage you to try it. The challenge with the transformer is the compute cost doesn't scale nicely, right? Remember, we're applying this. Remember, like, this is the little bit mind-boggling thing here, right? You're applying this for every single parameter at every single update step. So you're going to do a lot of computation in the transformer, and the small LSTM scales much, much nicer, specifically in sequencing, right? So we're conditioning on the entire sequence. But this is a great suggestion for follow-up work. I will assume everyone is understanding me. Yes? If we're providing all these things, aren't we just learning the second derivative? Well, I mean, of course, it could estimate that internally, right? Ooh, is it what's actually happening? It's another good suggestion for follow-up work, which is what does this thing actually learn? We have no idea. Just don't know. We just know that it works. So if you're curious to find out what it does, I encourage you to load the model. It's all open source, it's all there. Play with it and see if you can just approximate this with a second order optimizer, right? And obviously, second order is expensive. We're not providing a second order, right? So it would be approximate. Even how to approximate the second order from the first order is itself, a problem you can write many things about. So we try to focus on the three different things. As I said before, plasticity loss. You've probably heard of this. This is continual learning, right? Plasticity loss. We all know this. As you go through life, gradually, we get much, much worse at learning new things, right? Probably at this point in my life, I've lost most plasticity in my brain. The next second half will just be sort of kind of whatever. And we also have to balance exploration and exploitation because obviously we're doing reinforcement learning, not supervised learning, and it's non-stationary because as we're getting better at doing things, the world around us is changing. And these were the things we wanted our optimizer to be able to address. And we basically went back through literature and asked what kind of features have people used to measure these things. And then we feed the features into the optimizer as scalar values at every training step. And that's where the name comes from, open. Optimization for plasticity loss, exploration, non-stationarity, and also red, wonderful, open. This is a little animation that shows you what this actually looks like, but I think by now we all get it, right? I have my optimizer that I'm learning, I'm blasting this out, I'm training an agent, an entire training loop with this agent. I'm doing this many times in parallel. I aggregate the results to estimate the gradient of the meta-learner, and then I update my meta-learner and I repeat, right? So a vast number of agent interactions taking place for every meta step, and then we train the entire meta-learner using this. I think I'll skip through this quite quickly in the interest of time. Hopefully no surprises. The environment and the agent are training together. We use the optimizer to train the agent until the end, get the final returns, and we run our meta-learning step. This should be all sort of quite straightforward. Now, does it actually work? So first of all, we can actually, we can overfit to a single environment. So if you look at these environments here, in Minitar, we beat all learned optimizer tried to overfit to these environments before. So no learned optimizer has managed to do better than us. And we also beat a well-tuned Adam on these environments, on each individual one. And this is, now you might still thinking maybe you're just outputting the perfect parameters for that one agent and environment combination. What we can also do is we can fit to many environments. You can train on entire distributions of environments. And you see that we can beat all these other optimizers, both in terms of the mean, the interquartile mean, which is a more robust measure, and the optimality gap. What was quite encouraging is that our sort of feature engineering, by going to literature and asking what things are useful for optimization and reinforcement learning, actually made a big difference, because it turns out if you do an ablation where you just remove those features, our optimizer doesn't work. It really needs to know about that state of the network that is currently in, the optimization step, to be able to train these agents effectively. Let's talk about generalization. That was a great comment earlier. So what we also tried is we've meta-trained this optimizer on the distribution of random grid worlds. And now we're going to meta-test the optimizer, which means running a training run on a very, very different out-of-distribution sample. And those are these different grid worlds that either have like labyrinth structure and so on and so forth. And we're going to compare to Adam being trained and tuned on these environments. And the second axe of generalization is that we change the hidden size of our network architecture of the agent's policy. So the agent is an RNN. We meta-trained the agent with a hidden size of 16. And then we scaled up that hidden size to avoid the fact that, again, this might just be architecture specific or parameter specific. And what you find is it actually generalizes better than Adam. So you can see we're beating Adam by 5% in distribution. But if you now use that same Adam value and apply the same learning rates, and you apply it to a 128 wide network, we are doing better, percentage-wise speaking, than Adam at these held out of distribution sets. And the same holds true if we're going to apply this to these other mazes I showed you, like 16 rooms, labyrinth, and so on. Across the board, this is more robust than Adam if you're just transporting over the learning rate from Adam being tuned in one environment and applied somewhere else. So to be clear, what we did is we meta-learned on this one distribution, and we meta-tested without any change to the optimizer, to those phi, on a different distribution. No learning rate tuning, no changes to the algorithm or the loop, which I think is an indicator that generalization is actually possible, which was quite surprising to all of us. Any questions on this? Yes. We haven't tried that. This is actually not super expensive. We could have done it, but in the interest of time, we didn't. It's a great follow-up experiment that I recommend to do. Yep. The inputs to phi, I talked about in quite a lot of detail in the paper. We compute statistics that people in literature find useful as measures to specify the problems of reinforcement learning, such as dormancy. Show of hands if you know dormancy in your networks. This I find surprising. I would have thought in continual learning, one of the key challenges is dormancy, that your neurons go dead. That is super surprising. It means it's interesting to see. So dormancy says, are your neurons getting knocked out, right? If you have a ReLU activation, are you in a regime where your neuron is never activated, right? It's a big problem in reinforcement learning, and the belief was it's because of non-stationarity. And I would have thought in continual learning, this must be something that people think about. Maybe not. But we feed numbers like this that we compute on the network activations, summary statistics that are inspired by literature into the optimizer. Cool. So yes. So the question is, this looks a bit like quality diversity. We have a single fitness axis, right? So unlike quality diversity, where you have a grid of fitness and you keep members in all the different boxes, we have a single thing we care about, which is fitness. So I think that's the main difference. You could expand this to quality diversity, but we try to avoid. The final return is the fitness, correct? There's just a single number we're trying to optimize here. The final return of the agent at the end of training. Yes. So there's, if you think about a grid, we have sort of like in quality diversity, so everyone knows, you keep a grid of qualities. Say, for example, you care about fitness and entropy as two different things, and you keep members on each of these blocks, for example, in map elites as a good quality diversity algorithm. Here we just have fitness. There's nothing else we're tracking. We just care about the final fitness. Yes. Oh, no, of course not. It's meta testing. Question is, do we continue to update phi? Obviously not. It's meta testing, right? We have meta training where we train phi. We have meta testing. We deploy the algorithm, the optimizer, to test its performance on how that sets that I just showed you. Well, phi is the optimizer. So usually if you do lifelong learning, I assume what you do is you don't update Adam as the agent learns. So I think, this gets into future work here. Can we apply the same methods to non-stationary continual learning? And the answer is obviously yes, right? So you can imagine, for example, if you're doing lifelong learning, as the agent interacts with the environment, you may want to change the way you update your parameters. And you could entirely and totally meta learn this and probably should meta learn this, right? If you ever get bored of trying to write down maths and you just want something that might actually, if you're smart and lucky, might generalize, then I recommend doing this kind of thing. Cool. So this is a paper we did. I will quickly show you another result that follows much of the same pattern, but takes a different tack. So we had a theory paper that introduced mirror learning, which is basically a theoretical framework that says, as long as you're optimizing a new policy to maximize the Q values under the old policy that collected the data, minus a penalty for how far you move away from that old policy, you will converge to an optimal policy in the long run. And the nice thing about this framework is that it describes a lot of the reinforcement learning algorithms you can think about in that mirror learning space. For example, PPO, A3C, and so on, are all endowed with theoretical guarantees through the mirror learning framework. But this begs the question, which is, what about all these other things that are not currently explored, but that also can be framed in that sort of mirror learning framework, and therefore will have guarantees? Because we had this question before, right? You're not learning in the space of things that have guarantees. You're just doing optimization in the previous paper. But what if we stick to this space? So by now you'll probably see where this is headed. We parameterize this drift function here as a neural network phi. And we made it so that this is complying with theory from the mirror learning framework. So that for any phi, you get theoretical guarantees of convergence to the optimal policy in principle on paper. And then we meta-learned it using ES. Okay, so this is the general framework. Hopefully this is clear by now. And the results were actually quite mind-boggling because what we found is it was only meta-learned on and it generalized robustly to all of these other environments. Just using that same drift function that we meta-learned on one environment, generalized to 8 others. And in this case, we could actually understand what this does, this meta-learning process, what it has discovered. So how much time do I have? 5 minutes. Cool. So who is in for a bit of an intellectual challenge in the next 5 minutes? 1, 2, 3, 4, 5. Okay, let's do it, right? Bear with me, this will be fun. Okay, so what we're showing you here, what I'm showing you here is a visualization of the PPO objective. Okay, so what we're looking at, is there a question in the back or somebody just stretching? Either is great. What we're looking at here is the advantage for a given state action pair and how far we are from the policy that collected the data. Negative on the x-axis means I'm taking the action less often than the collection policy, and positive means I'm taking the action more often. And what you see in the colors is the gradient of my objective. So red means I'm trying to increase the probability of that action, and blue means I'm trying to decrease the action probability. So what does this mean? I have an action A in a certain state that has a positive advantage, which means life is better than I thought. I've collected data with PPO, and I'm now asking, should I update my policy? And the answer is, positive advantage, you should update your policy, make that action more likely. I update, and here I stop to update. Why? Go outside the trust region, because PPO has a clip. PPO has a clip which tries to keep the agent within that trust region. Don't go too far away from the policy that collected the data. Likewise, down here, I have a negative advantage. I'm taking the action more often than I did in the collection policy. I reduce my probability until I stop. Again, the clip hits in. This is PPO. Instead, what we learned with our meta-learning approach, Phi, the loss landscape looks like this. And the first thing that jumps out is it actually has certain similarities with PPO, because there's a blue region here and a red region in the top left, right? And there's also some structure that is shared. However, when you look at it, there's actually a few differences. For a start, there's rollback. If you have an action that has a negative advantage, but you're taking it very, very rarely, much less often than the reference policy, you're going to increase the probability even though you have a negative advantage. We're rolling you back to the threshold where the clip would have kicked in that this thing has discovered. And the nice thing is when we found these results, we then found out that somebody had written a paper on rollback a couple of years before, right? So this thing actually rediscovered a feature that people in the field had already suggested as a feature to improve PPO. There's also cautious optimism here for positive advantages. And interestingly, because we don't have a strict line, interestingly, there's optimization, there's a gradient here, as long as my advantage is not too big. It's basically saying you can update cautiously if things look good, but they can't look too good. If it looks too good to be true, stay safe, because you don't win the lottery all the time. And then there's an aspect here of implicit entry maximization, where we're basically trying to smear out probability mass across. And then we have features that we don't understand at all, which are these regions in the middle where you have this sort of wave behavior going on. What we also did is we then went and said, what does this actually do? What does it mean? And we parameterized this as a closed form solution. And this is what this objective function looks like. And what you will find is this also generalized really nicely across different environments. So there's actually a drift function here that works quite well robustly across different environments. And this generalized far out of OOD, so we trained it in continuous control, and we tested it on these mini-time environments. I will skip through this. Last thing here is we made this thing temporally adaptive by feeding in the time step in training and allowing it to trade off between exploration and exploitation as it goes to training. And you can see that this drift function changes quite radically over the course of the training process. And finally, like all these plots here, we do much better at the end of this, right? So this is this temporally aware meta learner that can condition a drift function on where it is in the training process. And this beats everything that anyone had ever tried on these environments. We've done a lot more work, but I'm coming to the end of my time. If you're interested, it's actually just, I've given you a short slice to the infinite wonderland of things you can do right now, today. All the code is open sourced. So please do go check it out. And I would like to finish up by just sort of like quickly wrapping up what we've done. We are in the middle of this revolution. Things that are unthinkable are now possible. Every experiment here would have taken years before, and now we can do it in a few hours or a couple of days. So this is, again, if you don't find this shocking, then I'm at a loss, which happens sometimes. And we've provided tooling, environments, algorithms, and so on to make this really easy for everyone to build upon. And I think for anyone who's working on meta-RL, open-endedness, motivated learning, continuous learning, so I thought that was most of CoLLAs, because I looked at the call for papers for CoLLAs, and these were the keywords. But it sounds like there's something I'm missing here, because I think a lot of people don't work on these things. But hopefully it's still interesting. You should work on these things. And then what I didn't get to is I was going to introduce PQN, our simplified Q-learner, but I leave that for a future presentation. And with all of that, You know, not everything is brilliant. Obviously, there's risks here. We talked about this a bit. What if you can't fit the algorithm into this framework? Is there a risk that we might be overfitting? And how does all of this actually interact with agentic LLMs, where the forepass is so expensive that you don't care about the environment being on the GPU? So, with this, I'd like to thank you all for listening and for the brilliant questions to make this interactive. You can find out more on my Twitter or on the website foersterlab.com. Thank you all. We have time for one question, or are we kind of back?
So it was very interactive, so you managed to do that. I'm a bit afraid if I open the floor to questions, too many, but maybe we can have. And now no one dares to take the one spot. Is there?
I have a few questions here on the.
So you pick one.
Okay, I'll just pick one from the Zoom. Cool. So there's a question here that says, let's find the most dip. But the optimizer itself does not need backpropagation, was a question we had. There was a question in the chat where somebody asked, the optimizer, does that not need backpropagation? Any answers to this? What do we say? Yeah. Does phi not need backpropagation? The answer is no, because we're doing ES, right? Remember, we're using evolution strategies. It's a backpropagation-free gradient estimation algorithm based on samples. And therefore, we can optimize phi without using backprop. Do we need gradients at all? Yes, of course, because the optimizer takes in G, the gradient at time step T, as an input. So we do need backpropagation for the agent to estimate the reinforcement learning update, GT. Cool. So that was the final question. Thank you all again, and enjoy the rest of the conference.